today we're going to focus on corrosion, basics, and state-of-the-art. This is a long session, and I hope to give you a very good overview of the corrosion process, the way to mitigate it, the advances in materials and analytical methods, and hopefully leave enough room for question and answer time for everyone who's participating. So let's start by looking at corrosion. Essentially, it's all over. It's all around us in that we can see it from structures to ships to pipelines to different types of corrosion that we don't even see, but have a very national significance in that a big chunk of a country's GDP is used only to address corrosion. So, for example, it's estimated, and these are NACE figures. NACE stands for National Association of Corrosion Engineers. Anywhere from 5 to 6.5% of the country's GDP is used to address corrosion, and this can include replacement costs, development of new materials, costs for inspection, monitoring, insurance, litigation, and even loss of production, delays, and downtime. In fact, the little joke that I have is that there's only one other profession that costs as much in a country's GDP, and that is lawyers. Lawyers typically cost 6.5% of the nation's GDP. So that's a joke there. In terms of impact in industry, this is a good spread. You can see that many structures are prone to corrosion, and therefore its impact on different sectors are shown and summarized here. It might be a surprise to you that the military addresses a lot of corrosion issues, as well as sewage systems, drinking water, for example, municipal water. Whenever you drink, you can imagine, or use the sewage, you can imagine where it has to go, and these things are all over where big cities are present, and some of them are even 100 years old in terms of the original structure, and they need to be replaced. And for example, people have been using liners program to mitigate them without digging those type of structures. And here you can see also how corrosion refers to oil and gas exploration, production, mining, different types of refining needs. Automotive is actually a big factor in that a lot of metal structures on the road, as well as when we go to structures like bridges, different types of highway construction that are quite old and needs to be replaced because of corrosion. Now, asset integrity and corrosion can mean several things, but essentially what you want to do is you want to preserve assets and get the most out of it with as little cost as possible. But we all know that the total cost of ownership is not just getting the cheapest material, but getting the value for your money. In other words, you may start with a cheaper material, but over the lifetime of the material, you end up spending a lot on maintenance. And that is really the interest for corrosion and mitigating it, how you maintain what's originally built. On the other hand, people have, of course, used the premium of very good materials or even non-corroding materials at a higher cost in the hope that you don't have to spend as much for breakdown. So we are really talking about the total cost of ownership or depreciation of assets. What corrosion also is a matter of surface area. So if you look around us, wherever a carbon steel or a pipe or any metallic structure is exposed to the environment, you're dealing with corrosion issues that needs to be mitigated, and that can be in the form of coating, that can be the form of burying underground or insulation. For example, in the oil and gas industry, a lot of this natural gas and liquids have to be transported through buried pipes, even rail, and you can look at the figures there in terms of distribution, transmission, gathering. We're talking about thousands and even hundred thousands of miles. So really, corrosion is an issue very much tied to surface area, wherever you have an exposure to the environment or the bacteria, or stresses or cracking or hydrogen-induced cracking, etc. Not only are they corrosion problems, but they can also be hazardous or health and safety issues, as well as mitigating disasters. What is corrosion? Corrosion essentially is a destructive attack on the metal. Now, it may surprise you that this is actually taking a refined material to go back to its original state. In other words, when we refine steel, we're actually using ore that's derived from the ground. The ore is the lower energy state of the material, so rusting is basically going back to its original form. What happens is that you have an electrochemical environment where one acts as a corrodant or an oxidizing agent and the other is reduced. So it's actually a redox mechanism which can be further divided into an anodic and cathodic site. And also in the presence of a corrodant or a bridge, or the presence of, let's say, water and oxygen, to simplify it, causes corrosion. In other words, you need at least 3 elements for corrosion to occur. One is the material itself that needs to corrode. The other is the corrodant or oxidizing agent. And then the bridge, which is essentially water or electrochemical bridge that facilitates that connection. So as an electrochemical environment, this is, of course, going back to electrochemistry, in that a battery or electrolysis or generation of a bias voltage is seen as a positive event, or one side of the coin. On the other hand, corrosion is seen as a destructive event, even though we are dealing with a reduction oxidation mechanism. So electrochemistry is very important for understanding corrosion. You can see in this standard reduction potential diagram or chart where corrosion essentially is the displacement of an oxidizing and reducing species, seen in both ways, but you can actually rank them in terms of a standard potential. Let's say in this table, where the standard potential is that of a hydrogen gas proton, you can see the rank of iron being minus 0.44 volts, so that's the electrochemical standard potential as compared to hydrogen. However, zinc, which is used for anodic mitigation or replacement, corrodes more than iron, as zinc is a good sacrificial anode for iron. On the other hand, down the list you will see copper, silver, or even noble metals having better resistance to oxidation compared to iron. What you essentially have to look at the flow of electrons. So a simple galvanic corrosion diagram, as shown here, shows that zinc essentially donates the electrons. On the other hand, iron and copper, it's the other way around. So in other words, iron is corroded more than copper. On the other hand, zinc is corroded more than iron. So I hope that simplifies things for if you are new to corrosion. Another way to put it is in terms of breaking it down into several potentials or electrochemical equations dealing with that of the corrodant. So the corrodant could either be oxygen, proton, or another metal. Essentially, you need to have an anodic side and a cathodic side where electrons can flow. And I can go back to this diagram if you would like to do later. Characterize these materials. Well, of course, one can visually characterize them, but quantitatively, and what we do in our lab, and many labs in particular, to guess, to predict, to do a forensic analysis of corrosion is use electrochemistry, which is one of the methods that I'll outline today. Here, what you can see is a 3-electrode cell setup, which can be done in a potentiostat galvanostat setup, or an instrument that has capacitive properties where we can do electrochemical impedance spectroscopy. In potentiometry or a DC measurement, we can look at the conductivity, which is one way to characterize the sample versus its resistivity, or by looking at the energy level of the material, essentially a potential experiment, where here we can see a typical polarization or tackle plot, where we can characterize the potential versus the current. And by the way, this disposition or extrapolated allows us to compare different barrier materials or degree of corrosion. On the other hand, capacitive impedance / measurements enable us, for example, use a Bode plot or a Nyquist plot to predict the transport of ions, and then that transport or that barrier of transport can be broken down or modeled into a electrical circuit diagram as shown here, where we can include the capacitance, the resistance, and the impedance as part of the model circuit. And from here on, we can characterize the corrosivity or the transport of ions in and out of a coating or an analysis of an oxidized metal. So again, I would be happy to come back to this, except that we have so much to cover and I wanted to touch base on some of the basics. One may ask, well, what are the different types of corrosion? Well, visually, one can look at them, but of course, one can employ either microscopy or spectroscopy methods. And in common language, people distinguish uniform corrosion, pitting corrosion, stress cracking corrosion, etc. What do we really mean by that? And the easiest is to look at this list where we can have a general definition of what these different types of corrosion are. So for example, uniform corrosion is what would be expected of a metal surface that is exposed to a normal environment, quote unquote, which can be expressed in the loss of material. Pitting corrosion is a metal loss that is randomly located on the metal surface, and this can be aggravated by the presence of acids or, for example, stainless steel and acid. Galvanic corrosion is when you have contact between two different metals, which can be correlated by their electric potential. Crevice corrosion, concentration self-corrosion, these are corrosion attributed to cracks, to crevices, to area you have higher concentration of corrodant. Another example is graffiti corrosion, which can be loss of carbon on the carbon steel, thus weakening the metal. So these are some generally, one can classify them in terms of their location, extent, or zone of redox reaction or method of delamination. And these are general terms that are often used by corrosion specialists or inspection monitoring programs that allow them to classify them in terms of their mechanism. Now, one corrosion mechanism that, again, is quite complex or too long to explain given our time is microbially induced corrosion. Corrosion, for short, can be caused by bacteria. A very common one is a sulfur-reducing bacteria that in an anaerobic corrosion rates, the metabolism is such that you form different oxidized species as well as both anionic and cationic, the sum total of which is that the biofilm that is formed further increases the amount of concentration of, and hence you have local deterioration. And this is dangerous in the sense that this cannot be easily seen. It can be tested, different species are available, but one of the best ways to reduce them is to use biocides. Corrosion under insulation is a type of insulation that's quite common in that the environment under the insulation is not observed, obviously, but the geometry and the way the insulation can be penetrated as a barrier material can result in accumulation of moisture, water, or other corrosion species, resulting in a local concentration and hence unseen type of corrosion. For example, there are many ways to detect this, but in principle, one can look at, let's say, the thermal signature of a coated or insulated pipe, which allows you to see where the corrosion has already taken place. So in other words, CUI is a corrosion where basically you can only do forensic analysis, and very little way of preventing it except that you have to maintain hermetic sealing or integrity of the insulation. Now, how do we prevent corrosion? Preventing corrosion is simply removing one of the three elements I mentioned earlier, which could be either removing the corroding material, removing the corrodant, or preventing the contact of the corrodant with the metal. Hence, coatings is a very important part of corrosion mitigation. So in coating a material, what you want to do is to prevent the electrolyte from reaching the metal surface, and this can be in the form of a monolayer film, or it can be in the form of a thick paint coating, or even a passivation of a thermoplastic, or even the presence of a sacrificial material. And of course, preventing corrosion can either be cathodic or anodic in methodology. So essentially, as a barrier material, you prevent the corrodant from reaching the metal, and this can be in the form of a material that is ultimately sacrificed, a material that is hardly impenetrable, or a material that is generated to form a deposit as the corrosion or corrodant action assumes the redox relationship with the material. What I'm talking about are corrodant or anti-corrosion additives that can be actively generated to form a thin film during the mechanism of corrosion. So a simple one to talk about are sacrificial anodes. Hence, a good example is zinc. Zinc, as you can see here, has a higher oxidation potential. So if you look at the EMF value as shown earlier, zinc will be oxidized first before iron. Thus, zinc as an oxidized material will transport electrons to iron, and hence it will eventually be consumed. And so zinc anode has been used even today on ship hulls or different structures, or the use of other metals such as magnesium has been used as a sacrificial anode. And this has been used from structures all the way to even semiconductors. Now, corrosion can also be prevented, and this can be done very early on as the structure or the asset is generated. This can be in the form of design consideration, or looking at the material compatibility, that is preventing anything that can result, let's say, in galvanic corrosion or using the same material all throughout, or proper design in terms of geometry, flow, and function. First of all, the general rule is to use the same material all throughout the structure, if you can do that. And here is a simple diagram that shows the corrosivity or the corrosion activity from graphite to galvanized iron. So for example, mixing copper and galvanized wrought iron means that you have that much difference in the half cell potential, and therefore direct contact would result in local corrosion or galvanic corrosion. Now, other types of material compatibility issues is not only galvanic, but also in terms of the environment or the temperature range, or its ability to facilitate flow. Hence, the material compatibility issue has to be paired with the intended purpose, either as a pipe structure or a metal sheet structure. So what about shape and design? What about fixing the geometry right from the beginning? So I could refer to this diagram, which shows that crevices or areas where you have local cell concentration, which people call crevice corrosion, are areas where essentially very little flow is occurring, or you can have a higher corrosion of the corrodant in that area. Hence, it is an area that necessitates closer scrutiny for inspection, and at the same time, it's almost predictable that more corrosion occurs in that geometry, or any particle debris or deposit that adheres to a surface. So for example, with pipes, you want the pipes to be as smooth and as laminar flow as possible, or smooth enough or lubricated enough so that you will prevent deposition of debris, because a debris that deposits on the wall of a pipe is essentially a source of corrosion or turbulent flow, as shown here, which can accelerate corrosion. In fact, flow velocity is correlated with corrosion rate. So as you can see here, the more cavitation, the more turbulent flow you have, the higher the corrosion rate. In fact, erosion corrosion simply means that you have turbulent flow, but you can also have particulate material that is part of your fluid corrodant. Another is the environment. So when we talk about the environment, we are looking at the presence of moisture. We're looking at temperature, as you can see here, because of the Arrhenius relationship. with the equilibrium, the higher the temperature in general, the higher the corrosion rate, and the more chemically degrading or oxidizing the environment is, the higher the rate of corrosion. Another is you can look at humidity. So very clearly in tropical environments or areas where you have high humidity, you have higher rates of corrosion, or simply just the quality of air. So an industrial air versus a rural air, you can see the differences in the uniform corrosion rate for these various steel products. Now, this can actually be simulated and predicted by predicting the availability of ions or the oxidized states at various acidic conditions and potential. So this one is an example of what we call a Fourier diagram that shows you the distribution of species of iron and its oxide at various pH conditions. So very clear here that under acidic condition, you have more corroded material, or in other words, low pH or acidic conditions tends to shift the potential such that you have higher corrosion rates or higher corroded material. Now, let's start talking about materials and the way we can mitigate corrosion. One way, of course, is to look at metallurgy as a solution. That is the use of corrosion-resistant alloys, whether it be in the type of grain or distribution of metal species or dope metal species, or the percentage of chromium and other less corrosive species that can actually not only improve the corrosion resistance, but some of its mechanical properties like modulus and flexibility. This can be done essentially by alloying. And many metals can be alloyed, can be thermally cured or annealed. Many types of corrosion-resistant stainless steel, as shown here, with different types of terminologies like Inconel, Monel, or Incolloy. Essentially, the incorporation of more chromium enables it to withstand SAR type of corrosion and higher temperatures or pressures. But this is simply looking at the type of metals that can serve as a sacrificial or a barrier protection to steel, which with a simple chart like this. Of course, titanium is a good compromise, an expensive proposition. It's lightweight, but also corrosion resistant. On the other hand, many corrosion resistant alloys will do the job, but the problem is they're expensive. And of course, not everything can be made of gold unless you go to heaven. Here, we have to then go to another route to protect corroding metal parts by going to coatings or smart coatings. Smart coatings can be used in many ways, not only for preventing corrosion, but preventing wetting, staining, thermal stability, etc. So smart coatings means smart paint. And smart paint means that you need to look at the application of paint, whether it's spraying or thermal spraying or powder coating, etc., on different structures. And of course, this is a cost-performance ratio benefit. So, for example, the refining, the pipe industry, and many types of manufacturing rely on corrosion-resistant alloys as well as different types or qualities of paint. Coating can be done either by spraying, brush painting, electrodeposition, thermal spraying. In fact, all of this requires very careful surface preparation with standards that are used to evaluate the effectiveness of the surface preparation and the coating method. As far as polymer-based coatings are concerned, one can use polyurethanes, fluoropolymers, epoxy. On the other hand, metal powders or thermal type of spraying can make use of zinc, aluminum, magnesium, and other metal oxide materials as well. So this is one way of mitigating coatings. Now, in our lab, and this is what we focus on bringing in nanotechnologies for the coatings industry, we focus on two things. One is the creation of more superhydrophobic structures. And we have proven that better superhydrophobicity or even super oleophobicity is very good for preventing corrosion as well as self-cleaning properties. For example, we published some papers where we have textured the coating using polymeric particles and a conducting polymer to have super hydrophobic effect. And both the polarization and the impedance analysis showed that these are very stable coatings at higher temperatures and a range of pH up to 2 weeks. On the other hand, a very thin layer or even one layer of graphene is enough to prevent this copper from being oxidized versus a copper that has no graphene layer. So this one monolayer of graphene is capable of acting as a barrier against the diffusion of oxygen on the other side of the coin. And lots of interest of this, of course, in the semiconductor industry, as well as additives for different types of barrier coatings. Smart coatings can also mean self-healing coatings. So in the case of a coating exposed to the environment or scratch or corrodant reaches that of the metal to be protected, a smart self-healing coating can have a mechanism to release inhibitors or release sacrificial material that then can be used to restructure or modify the surface by releasing those inhibitors, and or an autonomic healing in which you have diffusion or even polymerization of a material to reheal the coating. Thus, you prevent one element, again, of the corrosion trinity, which is basically preventing the corrodant from reaching this steel or the metal material in the first place. So we have lots of work going on in our lab. In fact, we're working with several companies on this area, including inhibitors on various waterborne and solvent-based coatings. And then, of course, all the analytical tools that I'm going to show you later, which is very important for evaluating the effectiveness of this barrier material. Sometimes it's really a matter of, again, the cost-performance proposition. So many types of companies would like to employ the cheapest available paint and then repaint it the next year and the next year and the next year and so on. So that means a proposition where you will have an initial low cost but a high maintenance cost. On the other hand, some type of coatings are expensive indeed, but after the first application, very little maintenance is used. And so those type of two propositions is essentially a value proposition. A lot of people overlook the total cost of an ownership, and this goes for both the metal, the structure, and as well as the coating. Now, an alternative, of course, is to have no metal at all. And the oil and gas industry, for example, or even refining and manufacturing industry is interested in replacing metal with non-metals. And the only material or the material that is most capable of meeting or competing with the cost of carbon steel is, of course, thermoplastic material, meaning something that can be produced as cheap as polyethylene or polypropylene. And of course, to have the mechanical or thermomechanical integrity, they have to be extruded as pipes, and the inside of a pipe can be, a metallic pipe can be coated with a thermoplastic or a thermoset as a coating, or essentially the whole pipe itself can be replaced with a polymer material. Now, what are our choices? Well, in the area of polymers or plastics, one can look at the value chain in terms of performance. The commodity plastics such as polypropylene, polyethylene form a base of this pyramid, and in other words, you can say these are cheap, very readily available plastic, and they're a good competition if they can versus carbon steel. On the other hand, many types of thermoplastics or even thermosets are what we consider engineering polymers. These materials perform very well at high temperature and high pressure. Of course, corrosion is mitigated, very high fracture and fatigue resistance, chemically resistant as well. The problem is these polymers are expensive and sometimes hard to process. This includes polyether ether ketone, PEI, polybenzoxazone, imidazole derivatives, okay? For example, polyether ether ketone or other polyether ketones are good substitutes in that they are thermoplastic in the sense that you can heat them up, although at a high temperature, so that they can be molded and actually replace metallic parts. And several companies are producing this. Polysulfones, polyether sulfones are very good polymers, high melting point, very good distortion properties, low water absorption. And again, these polymers are used as metallic replacements. And then we also have polyphenylene sulfide, which was recently bought by Solvay. Again, these polymers are tough, resistant against chemical attack, high temperature and pressure stability. They're harder to process, but they are commercially available, and there are many more out there. So these are what we call non-metallics, or essentially metallic replacements where you don't have to worry about corrosion. So the last part, we'll focus essentially on methods, corrosion testing, standards, and advanced monitoring. So a metal environment is exposed, metal in its environment is exposed to various temperature, pressures, chemical environments. So the operating condition is such that the metal surface, the way it's formed, whether you're looking at the grain boundaries or the presence of defects, the size of the grain or crystallinity, all play an important role in corrosion resistance, as well as give an indication of the extent of corrosion or forensic analysis. So we need to have an asset integrity management program, inspection monitoring, as well as different tools to do the job. Here is just a table summarizing the corrosion testing methods, where one can classify them in terms of accessibility, non-accessibility, its ability to detect cracks like defects, or its ability to detect general corrosion and pitting. And the table is summarized here. Ultrasonic inspection, eddy current measurements, liquid penetration experiments, acoustic emission, field signature method, essentially a combination of spectroscopic, microscopic, acoustic, electrical or impedance resistance measurement, and so on. So let's revisit that of the electrochemical testing method. In an electrochemical testing method, the ECS is to plot the potential versus current or current density. One can attribute the position and the extrapolation of the current into the I-core and E-core values, in which the movement of this graph here, for example, of the cathodic and the anodic part of the tactile plot can give us an indication of the corrosion resistance or the extent of resistance. On the other hand, a bolt plot and a Nyquist plot allow us to look at the species or the penetrability of the corrodant on a coating material, or the extent to which corrosion has occurred. Again, I'm going to defer the proper interpretation of this, since I really just want to survey the different electrochemical methods here. And a lot of instruments are available to do this. Essentially, what you want to have is one that's capable of potentiostat galvanostatic measurements, or another that's capable of impedance measurements. Now, another key tool is spectroscopy. Scanning electron microscopy is a good way to look at the morphology in the presence of corrodant, corroding species, or the mechanism of corrosion. One can go to high-resolution SEM. Essentially, a conducting material like steel need not be sputtered, but this allows you, for example, to combine it with EDUX and other types of elemental measurements that can characterize the corrodant species or changes in the metallic structure. So very, very useful tool. Another upcoming tool that we use a lot in our lab is atomic force microscopy. the importance of atomic force microscopy is this is a surface probe analysis that actually allows you to look at the corrosion environment in situ. So for example, a cantilever tip here can be designed to do an electrochemical experiment such that it can act as an anode or a cathode on a metallic surface. But for the most part, the easiest way to use AFM is to visualize or classify the size or the grain on a metal or the distribution of corrodent species on a surface. And we, again, routinely use AFM for corrosion analysis. A very X-ray diffraction. It's essentially used for looking at the crystallinity and the changes in the crystallinity or diffraction of your metallic material or even the polymer material. Instead, in terms of stress analysis, one can look directly at stresses caused by the welding procedure or stresses caused by different environments at high pressure and so on. So again, a very useful tool for looking at the corrosion of the metal itself. There are many more. In the interest of time, I'll go to the inspection, but essentially there are standards out there that outline the procedure for preparing, testing, and corrosion reporting. So for example, NACE has many standards, but keep in mind that ASTM has a lot of standards for testing metals, as well as ISO. SSPC is big on corrosion coatings, as well as NACE. Even the API has particular standards. Now, standards are not absolutes. These are essentially industry or committee-led procedures that is valid for a particular performance or environment, which provides a common language for companies to evaluate performance. But these are not absolute in that some of these standards overlap, and you can have your new standard or revisit the old standard over time. What we are dealing with is essentially managing corrosion. So from the perspective of a capital expenditure to the operational expenditure, it's a matter of decision making. One can utilize a more corrosion-resistant material, a better design engineering at a higher cost, but the trade-off is you have a lower maintenance cost. On the other hand, one can use a lower cost, lower material, but then expect to have more maintenance. And sometimes the economic cost is not the replacement, but the downtime of the production or the facility. And again, over time, you can have problems in terms of changes in the environment, whether it's increasing CO2 content or decreasing pH or higher H2S content. These things do change over time, and sometimes corrosion management is simply detecting the changes or changing the program as a reaction to these different parameters. Now, what I will do is give you an overview of what some inspection methods are used to evaluate the extent of corrosion or even do forensic analysis even in the field. Easiest way is, of course, to record the corrosion activity as a function of time, or using borescopes or cameras that allow you to access areas that are very hard to access, or even an online monitoring system that transmits the images remotely. There are ultrasonic testing methods that can be used to quantify the extent of corrosion or the effectiveness of a coating material or detection of flaw. This can actually be arrayed. So you can have one site ultrasonic testing, or you can have an arrayed site, which gives you a sampling of a large arrayed area that can allow some type of mapping. One can do radiographic testing. This is a type of X-ray, if you will. It's non-destructive, but the caveat is you have to bring a big instrument in the field. But it allows you to use radiation or even types of high energy to produce an image that allow you to evaluate the extent of corrosion without opening up or even deciding on a replacement, not until you know the extent of damage. In eddy current testing, one can utilize eddy current or flow of electrons to mitigate or to understand the extent of corrosion over longer areas. And I'll explain a bit the principle behind it. Now, maybe what I can do is relate to you problem vis-a-vis the testing method that can be used to evaluate. For example, CUI. One of the best ways is to do thermal mapping or radiographic testing. Heat exchanger damage can be evaluated by eddy current testing. Boiler tube hydrogen damage, in which it's very hard to access without a borescope or a visual inspection, will allow you to observe that problem. Turbine blade erosion, a simple visual inspection with a remote camera as possible. Offshore riser sand erosion, in general, a lot of coatings can be evaluated by sensor ultrasonic testing, or larger areas can be accessed through phase array UT testing. Again, radiographic testing can be used to look at areas with an instrument, to look at, let's say, flow-assisted corrosion utility in a steam pipe. Creep of high pressure in a steam pipe or even air fin fan problems can be detected with UTPA or eddy current testing, respectively. Compressor blade damage, refractory vessel damage, this can be observed by visual inspection. Weld heat affected zones can be inspected by radiographic testing. Okay, so these are traditional inspection methods which can be recorded, evaluated, continuously monitored, and set up as a program which can either be a risk-based inspection or periodic-based assessment. CUI, as I mentioned, is a common problem, and these are some of the techniques and their advantages and their specific parameters that can be tested. Again, I'll be happy to go back to this table. So lastly, what are some of the other state-of-the-art corrosion testing methods? So let's look at some of these mechanisms. So in an ultrasonic pulse ecosystem, essentially it's like sonar. You ping it, you get back the signal, okay? And you look at it in terms of pulse or time delay. Another is an acoustic emission analysis, in which you again look at the pulse rate or the amplitude average with respect to time. So you measure the current. In the thermogravimetric detection method, you can use heat or heat signature or the convection flow of heat on a substrate to look at the extent of damage or coating integrity loss. A meandering winding magnetometer sensing method is again an instrument that allows for non-destructive testing, which gives you an array, a map that can be used to investigate the extent of CUI, mechanical damage, or stress corrosion cracking. In fact, the stresses or the corrosions which you do not see are quite dangerous, because the problem is they can result in catastrophic failure as a function of the damage that is unseen but is actually bigger than what was thought before. In corrosion detection using a fiber optic acoustic emission, this one allows you to determine again wide range areas using a Doppler type of effect. Again, in the interest of time, I cannot go over this, except that most of these large field equipments are not easily owned by companies or production sites, but are rather rented, or you need a specialist to implement them and interpret it. In a laboratory, one can do experiments to measure eddy currents, and that is you essentially look at the, let's say in this case, the extent of atmospheric corrosion control on a steel sample. So actually, I don't have any conclusion slide, except that right now I want to leave some room for questions. So I hope this seminar has given you an overview of the basics of corrosion, the methods of mitigating it, the methods of inspecting it, the alternative to non-metallics, as well as an overview of coatings. And with that, I'd like to thank you, and I'd be happy to answer any questions.
Again, thank you very much, Professor, for the comprehensive take on a topic that's pertinent to so many industries and facets of everyday life, especially now in the contemporary society. I have started to see some questions trickle in on the questions module, so please keep those coming in. Now we're going to go ahead and transition to the designated Q&A session for today. Just as a reminder, if you came in late and would like to see the entirety of this session, our marketing team in Korea should have the recording of today's webinar uploaded to parkafm.com via a YouTube link, and you'll be able to see the parts that you missed if you came in late, or if you just want to review the session as a whole, it'll be there in perpetuity. So with that aside, let me go ahead and get to the first question here. This question reads, when utilizing graphene as a coating enhancer, what kind of life expectancy could be expected of that coating? And since it might incur higher cost, will that high cost be offset by a possible long life compared to other high-performance anti-corrosion coatings?
Good question. The graphene oxide can be produced several ways. One is with a chemical vapor plasma type of method to produce monolayer graphene. On the other hand, graphene and graphene oxide or reduced graphene oxide can be produced in solution or dispersion by exfoliation of graphite. The latter we actually use a lot to form composites with several coatings. And the main thing is to use them in a barrier configuration. So in other words, the more they're oriented flat to the surface or parallel to the surface you're protecting, the better their action is. In terms of mechanism, depending on the state, redox state of the graphene, it can be oxidized over time. So we found, for example, reduced graphene oxide to be, of course, effective in preventing corrosion, but the problem is they're not as easily processable as the graphene oxide. So in terms of cost, I've seen the cost lowering. In fact, in our lab, we prepare our own graphene oxide. So your starting material for our dispersion method, for example, is simply an oxidizing agent such as KMNO4 and graphite chips, and we exfoliate them through both mechanical and sonicating methods. So in the future, what you'd see is the price of graphene oxide dropping down, the improvement on its application towards barrier coatings or direct deposition on metal should become more effective.
All right, very good. Let's see here. If you're wondering how to put in a question, again, there should be a chat or questions module loaded in your control panel. Go ahead and send it in there using your keyboard. Today, everybody is in listen-only mode, so the keyboard's the only way you'll be able to put that in. We'll wait a couple of moments for the next question to come in. If not, we'll be closing shortly. One question for myself, Professor, since Park Systems is an AFM company, I know that you mentioned earlier how you were using AFM on a slide to evaluate the causes of corrosion in particular samples that came into your lab. Can you elaborate a little bit more on that?
Yeah, it's a good question. We use the AFM to design model corrosion mechanisms so that we can understand the way we prepare the coatings and its effectiveness in preventing transfer of ions and so on. So what we do is we essentially use the AFM, first of all, as a morphology or topology tool to characterize the coating material. Then the other is we apply a bias voltage in an electrochemical setup where we induce corrosion at specific areas from the tip of the cantilever, and then we measure the transport or the electrostatic map or the conducting map of that area. So in that way, we can measure it as a sequence or a period of time or concentration of corrodant. And the reason we want to be that detailed or even that level in terms of investigation is that it allows us to, let's say, understand the short-term and long-term mechanism of corrosion, in that if we can prevent as much of the short-term mechanism from occurring by design of the material we are preparing, the more we can improve its barrier properties as a coating. So again, that's one. The other is AFM. We have been using it as a forensic analysis. Because unlike SEM, AFM, you can use various contact and non-contact modes. It's a surface probe measurement, meaning you have surface forces, whether it's the stickiness, viscoelasticity, lubrication, or indentation mode, that allow us to probe the change in the grain boundaries or defects that are occurring on the metal itself, or if the thermomechanical integrity of a coating is compromised. The AFM allows us to compare the difference before and after the exposure to the environment. So AFM gives us that detail that enables us to design better materials.
All right, excellent. Thank you very much, Professor. We do have one more question, and it's related to the assets or the material that was presented today. Just as a quick time check, we have about 3 minutes left in the session before we'll have to sign off, but let's go ahead and address this question that came in. In addition to the recording, which I mentioned will be distributed via parkafm.com, via YouTube, the slides for today, Govette, will this particular set of slides, will they be the ones that we'll use for distribution to the attendees today?
Yeah, well, of course, the video recording is available. I would, as far as the slides is concerned, people can individually email me regarding the request for the slide, and I'll be happy to answer.
Wonderful. Okay, so in that case, if you could help me out here, Professor, and return to your title slide, that'll give everyone your email address. For those of you who have something to write down, you'll see that it's going to be rca41@case.edu, and that's how to contact the professor directly. If you have any questions or requests regarding today's session, I'll also put up my email address in the community chat. Hopefully you guys can see that. It went out to the entire audience. If you have any questions regarding this particular session, the webinar series that we hold on nanomaterials monthly, we will be holding another topic that will be announced shortly next month. So keep an eye out on that. Again, it'll be with Professor Advincula. If you have any interest at all in any of the other topics, the wide gamut of topics that we've covered so far in this webinar series, again, they are all available at parkafm.com. If you go to the Nano Academy section of the Learning Center, they are all there, ready for you to view at any time. With that in mind, no other questions have come up from the audience, so I think we've come to the time for parting thoughts. Any last words for today, Professor?
Yeah, Gerald, thank you, and thank you for the audience who stayed throughout and listened to the webinar. Essentially, this is a series that I have crafted with Park Systems to deliver content that's hopefully relevant to your particular research and industry needs. Today's topic, it may sound basic, it may sound like quite useful for some, and for others maybe again too basic. I really meant to survey the whole corrosion aspect as a field, in that there are many elements related in terms of both the materials, the inspection, the development. But anytime, I'd be happy to communicate with anyone in the audience on the state of the art of the things we do in terms of coatings and investigation methods. So this is a wide topic, wide range of all audience, and I really wanted to reach out to most of you, but at the same time educate those who are new to the field. So with that, again, thank you, and I hope to see you again next time.
Likewise, from everyone here at Park Systems, thank you very much for your time, everyone, and we'll see you again next time. Keep an eye out for the announcement on the next webinar.